Back in 1950, a British scientist quietly embarrassed the entire United States military. And he did it with nothing fancier than the algebra you learned in high school. The number the U.S. Army had locked away as top secret. He read it straight out of a magazine. July 16, 1945. Out in the New Mexico desert, the first nuclear weapon goes off. High-speed cameras catch the fireball swelling, frame by frame. And the energy of that blast, its yield, was one of the most closely guarded secrets of the century. Entered Jeffrey Ingram Taylor, G. to his friends and one of the great fluid dynamicists of the century. He wasn't at the test. He didn't need to be, because back in 1941, he'd already worked out the physics of a very intense explosion. The only thing he was missing? The data. Then the photographs were declassified. In 1947, a physicist named Julian Mack published a gorgeous series of them, the fireball at one instant after another with a distance scale and precise timestamps. So everything a physicist could want was sitting right there on the page. A radius and a time. So here's the puzzle. You know how wide the fireball is, its radius, at each moment in time. From just those two numbers, a radius and a stopwatch, can you recover the energy that set it off? Sounds impossible, right? Well, it's almost embarrassingly easy. The trick is to ask a simple question. What could the answer possibly depend on? Well, there's the energy released, the time since detonation, the radius of the shock front, and the density of the air it's plowing into, which we call rho. That's the whole cast. Now, we translate each quantity into its fundamental units: mass, length, and time. And that's the whole secret weapon of dimensional analysis. Every physical quantity is really just a recipe of mass, length, and time. For quantities, 3 dimensions. The Bakingemova PI theorem says there's exactly one dimensionless combination you can build. One magic number with no units at all. And here's the clever part. Since it has no units, it can't care what system you measure in. So it has to be just a constant. If that group is always the same constant, we can simply rearrange it. The radius grows like energy over density to the 1/5 power times time to the 2/5. Or, flipped around, the energy is roughly the air density times the radius to the 5th power divided by the time squared. And now the genius move. Take the logarithm of both sides, and the whole relationship becomes a straight line. Log of r against log of t, with a slope of exactly 2/5. So if the theory is right, the fireball data should land on a perfectly straight line. No fitting, no fudging. And the intercept? It secretly carries the energy. And when Taylor plotted the real Trinity frames, the radii from the photographs against their timestamps, the points marched up in a beautiful straight line. Slope 2/5, exactly as predicted. The physics was confirmed before he'd even computed a single number. Then comes the real prize. The intercept hands you the energy. Plug in a radius of about 140 meters, at 25 milliseconds, with the air density near 1. And out drops the answer. Roughly 17,000 tons of TNT. The real, classified yield was about 21 kilotons. So Taylor, armed with a pencil and some publicly printed photos, landed within a whisker of it, and then published it in 1950. The photographs were unclassified. The energy was not, and the U.S. Army was reportedly not amused. And get this, Taylor wasn't even alone. Von Neumann in America and Sadov in the Soviet Union cracked the very same problem independently. That's the quiet power of dimensional analysis. It lets the units themselves whisper the answer long before you understand any of the hard physics. Sometimes the shape of a formula is the secret.